Hello guys, we'll be doing transmission lines today, and as you can see I have a question set up in front of you. The two parallel pieces of circuit in light green are basically transmission lines, and one on your right in yellow are also transmission lines, and they're always represented in pairs. You cannot have them one piece at a time like you do for resistors, inductors, or capacitors. So over here we have like a bunch of circuit elements such as an inductor, resistor, and Z load. Z load could be anything. It could be your next part of the circuit, or it could be something kind of device that you connect to your existing circuit. And the Z in is the part kind of if you connect a different circuit to your circuit, and that's what the Z in or the impedance that the new system will see from your current existing system. Well, going on this, usually the best approach to start these problems is to start on your extreme right. And on the right, as you see, the Z load is given in, it has both the real and the imaginary part. It has got the 10 minus 5 J ohms. That's the impedance for the Z load. And in the yellow over on the right, you can see this is basically a short stop, and since we have to add these things together and come up with one collective resistance or impedance, we will first do the impedance for the short stop. The short stop could either be written as ZSH. This is symbol that we use for symbolizing short stop, or we can use Y shorts. I'll be using Y short, which is basically admittance. Admittance is nothing, it's just the inverse of the impedance, and we use admittance whenever we have to add the circuits which are in parallel. And I should write that this is parallel only. So the formula for Y short is basically negative J Y naught cotangent beta L, and your beta L is always given over here. Your length is 0.2 and your impedance is 100 ohms. So this can be seen as, like, this could be written as Z short Y naught. The Y naught is 100 ohms cotangent of beta L. You can see, you can consider this 0.2 as 0.2 times 360 degrees, because 1 lambda is 2 pi, and 2 pi is also 360 degrees. So over here, if I run these numbers, I'll just get J 0.003. That's my admittance from the short stop on the right given in yellow color. Now if we have to add this with our impedance, we cannot do it straightforward because our impedance is given in Z terms. So let's get this ZL in terms of admittance, which can be written as 1 over ZL. If I go further on it, it would be basically 1 over 10 minus 5J, or it could be written as 0.08 plus J 0.04. Always it's a good approach to add small pieces of information or your thought process. What I will do over here is I'll just mark where I'm looking into. If I look into my circuit from this part in, I should call it Y2, since I'm working with impedance only. Since I should call it Y2 since I'm working with impedance only. So my Y2, sorry, let me change the color here. Yeah, my Y2 would be basically the Y load, which is on the right in form of ZL, and the impedance of the short stop. this is my y load. So this is basically 0.08 plus, that is my y load, plus y short. Y short is basically negative 0.003 J. If we add these things together, we get 0.08 plus J037. That's our y2. We can always, it's always a good practice to put these numbers in Cartesian. This is in Cartesian form, which is, just on a quick note, it's basically a plus b j. This is the real part and this is the imaginary part, or it could be seen in polar coordinates. The polar coordinates are basically the magnitude of a and b, which I can say as like this, which is basically r, and the angle is given by this consideration, but it is always a good practice to check which quadrant you are in, because let's see if we have this is just a diversion from what we are doing, but I think this is important to review complex numbers over here. So the important part over here is, for instance, you have like -1, -2 J. So this is your A and this is your B. But as you see, if I put this in my calculator, it will not be able to differentiate between positive values, which is 1 plus 2J, 1 plus 2J. So it's always a good practice to remember this small rule. Let me get rid of this thing. Yeah, the small rule is like, whatever the angles that you have, just put them straight in your calculator, and if you get your anything, your phi is coming out over here. This is your phi. If it's in your first quadrant or the fourth quadrant, you don't do anything. But if you are over here in second quadrant, you have to add 180 to your phi, or just the pi. For the third one, you have to subtract 180 from it to get the angle from here. Well, or there are other ways of doing it. A simpler way, what I usually do, is just to use my TI-84, and I'll do a separate video to explain how to convert between Cartesian and polar using your TI-84. Well, so that's just that. Okay, now if I look at that, my y2 in polar coordinates would be basically 0.088 and 25 degrees. I did that using the calculator, and that's a separate video on its own. And now if I make that into my impedance, the impedance would be just an inverse of that. Or if I go straight into Cartesian, that would be 9.3 minus 4.3 J. If I look into further into my picture, I see that now I have to add the third one, which is at this spot. Since these two things are in parallel, now the circuit should look like something like this. It's the same circuit, we have just collapsed two of the terms. So this basically represents your Z2 altogether, which is 9.3 minus 4.3 J. That's this, and that's my already existing resistor and everything. Nothing has changed. Basically, it's just that we have collapsed two components on the existing diagram. So that's what it is, and it was given to be 9. The omega was 10 to the power 9. So now that I see that these two components are in series, I can just add them. And for adding components in series, I have to use a series circuit. So I'll keep them in Z. So my And if I say uh, on top, I already mentioned that. So this is my Z3. If I look into here from the left, this is a Z3 that I have, and that includes all the parts of the components to the right of it. So the Z3 would just be uh, yeah, Z3 would just be Z2 plus Z inductor. So the impedance for an inductor is given by j omega L, and as you can see, omega is already given to us, which is 10 to the power 9, and L is the value of the inductor, which is given as 2 nanohenry. 2 nanohenry is 10 to the power negative 9, which comes out to be very clean, just 2J. That's my Z inductance. So if I have to find my Z3, my Z3 would be just the sum of 2. Z2 was already 9.3 minus 4.3 plus 2J, which comes out to be 9.3 minus 2.3J. That's my Z3. Z3 is the circuit that we are looking in on the right. Now when we have to include the transmission line over here, we have to use a special formula which is not so difficult. It's just like once you get hold of it, it's easy to use. The formula is given as Z in equals to Z naught times Z load plus J Z naught tangent beta L over Z naught plus J Z L tangent beta L. So this basically this Z naught is the value of your transmission line, and this number is anything to the right of your transmission line. These two things, they are representing numbers on your anything on the right of it, and when you do all of these numbers, you get an output number, which is your Z in, or basically anything that you get when you are looking in from this side. Let's get back to the calculation part. So if I have to find my Z in, or I should call it my Z4, Z4 would be basically looking into the circuit from from the right at this spot. That is my Z4, and it should be pretty easy to calculate. It's if you just plug in all the numbers, it's just a matter of using the numbers. Since our line was given with 25 ohms, we'll use that number, and 9.3 minus j 2.3. This is this part. This part is basically ZL plus j 25 tangent, and then the impedance for our line was given to be 1.1. So 1.1 lambda, it will give you the same length as zero point 0.1. The extra one is not doing anything for you. So if you take zero point 0.1 of 360, it's basically 36 degrees, and I'll say tangent 36, that's in here, divide by z naught 25 plus j times tangent 36. It's easier to open these brackets first to before plugging it into the calculator. So what I do is just I'll put these numbers like this, and I'll add the imaginary part, and then I'll add the uh, real part to it. So this comes out to be basically 9.3j minus, because we know that j square is minus 1. So these two things give us a positive, j square positive 2.3, and all of this is basically times tangent 36 degrees. So when we solve all of that, well, I did it in using polar coordinates, and in the polar coordinates it comes out to be 18 with an angle of 60 degree, and on the bottom it comes out to be 27.5 and angle of 14. If we complete all of this together, we get a number like this, 16 degree, and this is in polar coordinates, and that is basically my Z4. Z4 is all the number that was looking in here. Now we have to work with admittance, since the total circuit at this point in time will look like this. It's just two elements together. The one that was already given to us, 80, and this Z4 that we did here, which is actually given to us in polar coordinates. So if I have to add these two things together, I need to use admittance. So admittance is basically Y4. I can use that Y4, and Y4 is just an inverse of this. Comes out to be 0.06, and the angle is just the negative of that, negative 46, which is in Cartesian it is 0.04 minus j 0.04. It's always a good practice to keep your numbers in both polar and Cartesian, because you might have to come back to these numbers when you're doing other kind of stuff, maybe when we are looking for VSRW or the reflectance in the line. So when I'm looking into it, uh, if I find my Y in, that is the admittance when I have to add my resistor of 80 ohms plus my Z4, or should I say my Y4. This comes out to be 1 over 80 plus 0.04 minus j 0.04. This this number is basically 0.053 minus j 0.04. This is my admittance. But we are in the original question we were asked for, one of the things that we were asked for was to find Z in, and Z in is just the inverse of this thing. So Z in equals to 1 over an admittance, which is basically 12 plus 9.5 j ohm. Always keep the units with it, because we will not be able to figure out what we are talking about if we don't have the units at the end like this. The next part that we are asked in this question is basically to find the Rn or gamma in. Gamma in, the basic formula is very simple. It's just like Z in minus Z naught over Z in plus Z naught. This thing has no units to it, because this is just a ratio, or it doesn't have any units that we use usually. And the Z naught over here is either it's given to you or it's assumed to be 50 ohms, 50 ohms for communication circuits, and we are basically only talking about communication circuits over here. So always assume to be 50 ohms if it is not given to you. Communication. So now if I add my Z in, which is given as minus 50 ohms over same thing, this comes out to be very simple number, 38 plus J 937 and 62 plus J 9.2. I can it's always a good practice to get these numbers in polar coordinates. In polar coordinates it is like this. We will have to use the polar coordinates later in the circuit. The final value for this is 0.62 and in angle of 157 degrees. That is the reflectance that I see at the end of the circuit. That is the reflectance that I will see over here. The reflectance that we will see over here. The next part that is asked in this question is VSWR, which is in other words also called the standing wave ratio. The standing wave ratio has formula as VSWR given by 1 plus 1 minus this, and this number is just the magnitude of your gamma in, and for us it was 0.62, so I'll say 0.62 over this 1 minus 0.62, which comes out to be 4.3. The good a good way to know if you're going in the right direction or not is this number always has to be between 1 and positive infinity, and the good numbers are between 1 and 2 something. That's what we use in the practical devices. After that, the next part is basically asking for the return loss. The equation for return loss is 20 log of gamma in, or just the magnitude of the gamma in. So over here it's 20 log of, which comes out to be 4.2 dB. You might be asked to find the reflection in the transmission line. For that, we use the similar equations, but at different location. So if you want to find the reflection in your transmission line, you will be basically looking at your circuit from here onwards. Let me mark it with yellow over here. From this point onwards. So anything to the right of it would be used in the gamma in formula, and any to the left of it would be used for impedance. So as you can see, the impedance over here is 25, and impedance to the right of this spot is Z3. And let's find out what our Z3 was. Our Z3 is this number. Our Z3 is this number. So let's do those numbers together. I should mark this number by gamma in or L line, so that we know that it's just for that line, and minus Z naught plus C naught. But if you look into this, this is over here in this question, it's given to be 25 ohm. Let me go back. Yes, as I already mentioned, it's given to be 25 over here, and we can use this number and any value that's to the right of the circuit. So to the right of the circuit, the part was Z3, which is basically 9.3 minus again we have to go into polar coordinates to solve this, and in the polar coordinates it comes out to be 15.87 and 171 degrees, and 34.4 and negative 3.8. Total would be 4.6, and the angle would be minus 167. Okay, if we are looking for VSWR for the line, that would be given by the same formula, gamma in over 1 minus gamma in, but this time I'll use the R for the line that we had before, just found out. And if we do this number comes out to be 2.7, and as you can see, There is no unit next to it. This is just a ratio. Okay, so the last part that we are looking for is uh, the Vmax. Vmax, these are basically the locations where your stunning wave has the maximum ratio. Your stunning wave could look like this, and that's how it is. And this is the location where you have your Vmax location, and we're trying to find that location. As you already know that we have mentioned that we need to see this spot as your the first spot for your transmission line, and we go back from it and considering that to be negative length. Now as we go down, we can work this out and we can find the exact location where the Vmax happens. The formula for that is basically x equals to minus theta plus minus 2n pi lambda 4 pi. This angle could be in radians, or we can make this into a 360 degree. For ease of convenience, I'll just use radian. So, and remember that we are working only with the transmission line. This Vmax is for the transmission lines. Vmax is for the transmission lines, and we will be using 167 degrees over here. And for the 167 degrees, I can make that into 167 degrees over 180 times pi plus minus 2 pi, and I'm considering that this is my n equals to 1, negative of this pi. That's my x1 location. My x1 location comes out to be negative 0.2, oh my bad, negative 0.27 lambda, negative 0.27 lambda. So if we have to find x2 location, we just have to do subtract half a lambda from that. So that should give us negative 0.77 lambda. And if we have to look for the third location, we can just do another negative half lambda. That is basically this negative half is coming from um, the next value for this. Sorry, my bad. Next value. So this over 2 over 4 is going to be just the half of it. 2 over 4 is going to be half thing. That's why we are having half lambda. But this number, if you look into it, this comes out to be 1.31 lambda. But the length for our transmission line was 1.1 only. So this does not apply. Only values that matter to us are x1 location like this and x2 location over here. That's about it.